Okay, so hopefully the audio isn't like messed up. Okay, I should be good. So the setup's a little weird today because I'm recording from not one of the normal rooms I'm in, so that's why you can't see me. But I think we should get along just fine. I'm sorry if like the video's a little out of focus. That's just kind of like how the recording works. It's just kind of bad. But that's fine. So today we're going to be going over like applications of integrals, more like physical applications, mainly involving like finding like the mass, like doing stuff with like mass and density. Um, so yeah, it's going from like density to I'm pretty sure, yeah. Wow, that's awful. Um, yeah, going from like density to mass, going from like force to work, as well as doing some like pumping things with like water. So like pumping, um, stuff like that. So this is sort of what we're going to be focusing on. Sort of to start out, similar to like what the textbook does, I want to start out by talking about the relationship of like mass and density. Those you can read all about it in the textbook, so I'm just going to sort of like skip to like the important part that you'll need to know how to use for like actually solving problems. I'm going to try to like bring. Oh my god. So how we do that is there's this like little basically a formula. So if we have some like uh, we want to find the object's mass, some object's mass. The way we do over like sort of a specific interval, if that makes sense. Um, we basically just take the integral using like that interval as the bounds, and then we assume that the density is some like kind of function of x, which we symbolize as like rho of x, and basically we just like integrate it. So this is for some density rho of x. So like it could so basically what this is saying is when we're talking about like the density is some function rather than it being a very constant sort of like uniform object where the density is the same all the way around everywhere it's in the object. We're trying to say that okay, it changes as you like sort of move throughout it. So say like we have some object that starts as like a rock, and then as you sort of move along it, it gets to be like a marshmallow. Marshmallows are pretty, they're pretty like not, they're not too dense, right? Like rocks are like very sturdy and very like all their atoms and stuff are like very close together. Whereas marshmallows or something like similar to that can like float. Or any food really, it's a little bit less dense. Um, so that's how I sort of like to think of it. And then this function basically is just like okay, if our rho of x was like x squared, well that looks like this, right? We'll say that we're only looking from interval from like here to here. Well, that would mean our density is really, really low here, but then it's really, really high here. So that would be like marshmallow to to rock, right? So try to picture like an object that moves like that. Whereas if we were sort of only dealing with the interval from here to here in red, that sort of goes from a high density to a low density to a high one again. So that would be more like rock marshmallow. Yeah, rock. So that's how I like to think of just like how densities might look different in objects, sort of as you go between interval. So to like do a really quick example, let's say that we have like a thin rod. Um, well, by thin rod, we really mean like it basically doesn't have like any sort of like radius, if that makes sense. This is example 6.23 from the textbook. What we're going to be doing is we have like a thin rod around x-axis between pi over 2 and pi. So x equals these things. Density of rod is sine x. So that means we're going to be dealing with like something like this. So we even get some negative density in there, which is kind of neat. However, since we're going from pi over 2 to pi on the unit circle, that's only from here to here, right? And sine is positive, is y, so that we're actually only going to be dealing with positive densities, right? Something to consider. And we want to find mass of the rod. Oh. Well, again, you basically just do what I sort of stated up here with the integral. There's nothing really fancy to it. You basically just take the values, you were given, and then plug it in. So if we want to do that really quickly, A is pi over 2, B is pi, we have sine x, dx. Let me just solve for this. So the integral of sine x is just cosine of x, or it's negative cosine of x, evaluated from pi to pi over 2, full pi over 2 to pi. And the reason we know this is because the derivative of cosine of x is sine of x, right? Because it goes to be like negative sine of x, but negative times negative is positive. So that's how you know that. This was going to be a negative cosine pi minus a negative cosine pi over 2. So cosine of pi, well, on our unit circle, pi is right here. Cosine is x coordinate, that's -1. So -1 times -1 is just +1. Minus, well, cosine of pi over 2, it's right here. That's 0. So I think that should be good. Yeah. So yep, that's our answer. So the mass was 1. Oh yeah, sorry. This is literally mass. My bad. This is density. Cool. Oh, I can do another. So literally all of the sort of mass density problems that you're going to be dealing with are that exact same formula. They're all pretty sort of self-explanatory, I'd say. There are also some other sort of problems that deal with sort of like mass density stuff of like circular objects. And so say that how should I say? The density function is given to you, but rather than it being just like a thin rod, which is just sort of like, something like this, but with like not really a mass, it's not really like a radius between like the x value, the x axis and like the rest of the rod. We're sort of just dealing with with something that actually has radius at this point. It's basically like a disk. Oh wait, let me like read over this. Sorry. Interesting. So yeah, there's a whole thing in the textbook where you can read about sort of like finding these. So this is sort of when we're dealing with finding masses of objects that sort of go long ways along the x-axis, whereas they give you another theorem formula basically for when you're trying to calculate something that's more like a disk, if that makes sense. So that's more when it's like sort of like this, I guess. And this is sort of like going like this way. So like the instead of having some kind of different mass from like here, from like going like this way. Like if we had some disk, then the mass, the density changes in this direction. Same with this direction. So like the density here would be different from here, whereas the density in like this circle would be different from like that circle. And so the way we do that is we find some mass. It's assigned to, so like our 0 is our starting point, right? And you go out to the radius, r, and you multiply by 2 pi x, where 2 pi x and then rho x dx. So this is sort of our density function. The 2 pi is sort of to get sort of all the way around that angle. And the extra I comes from, I believe, just the area of the disk itself, but I'm not sure, honestly. However, we can sort of like do one of these problems. So if we're given density function, a radial density function of root x and a disk radius of 4, calc mass of disk. So again, here's a disk. This is r equals 4. And then the density as it goes along to the outside edge of this follows the x, the root x path. So it slowly gets bigger. And so we can use that information using this formula. Oh, I guess you can't really see. Sorry. Okay, this is the problem. So of our disk, it has a radius of 4. We start from 0. And as you get to like farther outside circles of this, it follows this root x path. So the density slowly gets greater as you get to the outside of the disk. And we can use this formula that we have right here to solve it. So for the mass, so our radius is 4, 0, 2 pi x, we got root x. I'm going to rewrite this because we have some constants here, so we can pull these constants out. 4, 0. And then these can combine, right? Because this is x to the first, this is x to the first 1/2, and those can just add to be x to the 3/2. And then basically from there you integrate. So x to the 3/2, you add 1 to the exponent and then multiply by the reciprocal of that new exponent. So there's no integral, there's no sum there. That's gonna be 5/2. So x to the 5/2 times 2/5, because you multiply by this reciprocal, and that's evaluated for 4, 0. So you got 2 pi times, take your 4 in. Sorry, this is just like a lot of computation. I just want to like move on to other things. So I'm actually going to save us the trouble of like worrying about it. So this is just going to be dot, dot, dot. And you're eventually going to get 128 pi over 5. Cool. So, okay. Next thing we're going to do is like work. So say I have some object on a table. I want to move it a distance d. Be here. There's this concept called force, where I apply a force to this object to make it move this distance d. And I can combine these to create a new concept called work, where work was force times distance. So the work done to move this object using this force, this distance, is just the force times it multiplied by the distance. Okay. I also want to mention that forces have a lot to do where there's a cool application of them. It sort of goes into springs a little bit. So there's like a nifty little like equation that we can use to model how springs sort of work and like the force needed to compress them or stretch them. So sort of a baseline for how they work. We're sort of going to be dealing with a spring that's like this. Pretend this is all like resting. So this is resting natural length. It's on the x-axis. 0 starts not at like where over here where the spring starts, but it's at its resting position. Okay. So we can model the force required to keep a string stretched or compressed by some constant k, in addition to the distance. Not in addition, but it's also proportional to the distance that it is already like stretched, or the distance from its natural resting point. So it's this idea of like F equals K times X. Kind of important. Sorry, just making sure I have this all right. Okay, we're good so far. So in this, we have X equals distance from rest. K is a spring constant. In meters. This is in kilogram per second squared, but I don't think you really need to worry about that too much. F is force. Newtons. And W is the work in Newton meters, or joules. So these are sort of your, well, I'm trying to do that backwards. These are your, what's the word? Units for this. I wouldn't really worry about like these. I would mainly worry about joules and newtons and math and like distance. That's sort of what you're working with. So there's like a whole little explanation as to like why the next formula that I'm about to write works, but I'm not going to go into that too much just because I want to more focus on like the actual like problems and stuff. So we can sort of like relate like the amount of work done from up here, the work done to sort of like move a spring, like compress or stretch a spring, using an integral. So we can write that the work equals the integral from a to b, where a and b are sort of like the stretch distances, if that makes sense. And then you just integrate the force. And that's like a sort of a thing in physics where if you integrate force with respect to distance, you get work. So yeah, so kx dx. And this can be an uppercase or lowercase k. I'm sorry, my lowercase k's are weird. So this is sort of like the main thing you'll be looking at. And so a lot of the problems we're just going to deal with, okay, they're going to give you a lot of different values to plug in for these variables. And then you have a couple of different equations that you can use to plug in and find the missing variables that you're eventually looking to use to find like whatever problem, like whatever values you're inevitably looking for. So for example, if we have this problem, actually, I'm going to move it to the other page. Actually, I'm going to keep it here. So for the problem, say we know that 2 joules of work is needed to stretch a spring from its natural length of 30 centimeters. So that's one of their distances to 42 centimeters. A, work to stretch from 35 centimeters to 40. And then B, how far, well, I guess distance, a force of 30 newtons will stretch a spring. We'll stretch the spring. Oh, shoot, okay. So we're looking for a W for the work to stretch from 35 to 40 centimeters, whereas we've already found what it is from 30 to 42. And we know that the distance of a force of 30 newtons, and we want to know the distance of force of 30 newtons to stretch it. Well, let's think about the different like variables that we have up here and see if we can plug anything in. Well, we know that for, let's think about this. Well, something that we haven't given is a couple of different like distance values, right? So we have a couple X's. That's something important to keep in mind. We've been given a force in one of the problems. So we have like a thing for F. We're trying to find a work, right? And we're trying to find a distance. So we must get some values that don't give us the work, or that will give us the work, but we have everything except for W. Let's just think about A first. So yeah, we want all the different values, right? Because that's the only way that you can solve for different like equations, is if you have all the different variables for everything else, and then the one left over one is when you're trying to look for. So we have some X's, right? So we have some X's, right, for this problem. And we don't have an F, do we? Well, we know that we can calculate F by doing by using this X. So I mean, X right here, I guess, would be just like 5, right? I just want to make sure I'm doing this right. Yeah, it could be. And then because that's a distance between 30 and 45, 30 and 40, 35 and 40 centimeters. But we don't know a K, right? We haven't been given any Ks. We've been given sort of everything else that we can sort of like lead up to, but Ks have really been out there. So I think the first thing that we should sort of like try to solve for is K, because that's something that you can't really like use from anything that we've been given here. K is basically just a constant that is differs between the different strings. Springs that you're using. So we're gonna go to the next page. Should I write this out? So you want K. That's awful handwriting. I'm sorry. You want K. So we have a couple of different ways that we can find it. We have this one way where F equals K X, right? And then this other way where W equals integral Kx dx. Well, I remember that we weren't given any forces, right? We weren't given anything for F. We want to find an F, right? Oh, shoot. We want to, sorry, I'm like not given much room to do this stuff on. Okay. We're given an F for right here. We're given a force for right here, but that's like the second part of the problem. So I don't think that really relates to what we're doing right now. So I don't think this is really going to work because we don't really have a force. So what about this part? Okay, well, let's think about the things that we can plug in for. So we know that we have, okay, well, we have these variables A, B, K, and then X is what we're integrating. So we can't really plug anything in for that, right? So let's think about what these A and B's could be. Well, we know in the problem that we were actually given not only A and B's, but also we have this W in the equation, right? So in the beginning of the problem, we were told that 2 joules of work, so that could be for W, is needed to stretch a spring from its natural length of 30 centimeters to 42 centimeters. Well, that sure seems like a solid A and B choice, right? Because it's doing something from over an interval, right? So what if we sort of like plug stuff in? So we got like 2 joules equals, well, I already know like A and B are, I already know A and B are like 30 to 42. But because 30 is its natural length, we're actually mathematically going to pretend like it's 0 and then do everything based upon that. So if that's 0, that's 30. And we don't really want to work in centimeters. We're going to more work in meters because everything else, such as like x, which is what's necessary for the integral or for this formula to work, we're going to pretend like this is actually meters. So this is not 30 centimeters, but more like 0.3 meters. But remember, it's also 0 because we're starting from our natural length. So this is not 42 centimeters, but it's 42.42 meters. But because it's 12 centimeters away or 0.12 meters away from the starting point, we're going to pretend like it's a 0.12 in this integral. We don't know k. We don't need to know x because x is what we're integrating, right? So all we have to do, basically, just like solve. We have to solve for k because we know that once we integrate, we can just plug these values in for whatever x becomes, and then all that will be left is k because we have plugged something in for this w. So knowing that k is a constant, we have x raises up by 2. You multiply by the reciprocal of 2, so that would be 1/2. So we have 1/2 k x squared. Make sure I'm all good. Yep, and this is from 0 to 0.12. Okay. That equals, well, we're going to plug 0.12 in. So we have a 1/2 k 0.12 squared. And I would subtract from 0 plugging into here, but since it's 0, 0 is just going to make everything else 0. So this is all we're dealing with. So now we just want to solve for k. 2 equals 1/2 k 0.12 squared. I could multiply both sides by 2 to get 4. 12 squared. And divide by 0.12 squared to get k equals 2,500 for 9, which is kind of obscure, but usually k values are kind of like that. It'll just be like that. Okay. So now that we have k, let's go back to our original question. We need to know what the work is to stretch from 35 centimeters to 40 centimeters. Well, luckily we have this k already, so we can basically just plug everything back in and sort of do a very similar problem now, except instead of solving for k, we're solving for w. And we already know these a and b values because we've been given them in the problem. But we're not going to use 35 centimeters and 40 centimeters. We're going to use 0.05 and we're going to use 0.1, right? Because this is 0.05 meters away from the natural resting length of 30. And this is 0.1 away. So let's plug that in. W equals 0.05, 0.1, 2,500 for 9x dx. Let's think about this integration. Well, you can pull the 2,500 out, over 9 out. X goes to x squared, divide by 2, times 1/2 x squared. 0.1, that's a bad one. 0.05. Great. I would go through this computation, but because of like the fraction of weird decimals, I'm just going to write it out. it gets us to 25 over 24 is 1.04 joules, which is our final answer. Okay. So what about B? I want to know the distance to a force of 30 newtons will stretch this. Well, we're given force, and we want to find distance, and we know K. So maybe we can just go back to our original formula right here, right? I just kind of plug stuff in, solve for X. I feel like that would make sense. Because right here, we're dealing with intervals, right? And you can't really like get an interval back out of this integration, if that makes sense. So you can't really solve for the difference of A and B. You can solve for the difference of like something complicated. Sorry, I don't want to like talk. I don't want to go into that. But yeah, it's really hard. And since we're looking for just a distance, that's basically what we were doing up here, right? Where our work is F times D. And then we got this formula from it. So we know that force equals K times X. Which means that our force of 30 equals our K of 2,500 over 9, right? Times X, which is our distance. From here, we just solve. So 30 times 9 is 270 divided by 2,500 equals X. Pretty sure this is about 0.108 meters or 10.8 centimeters. Okay, just to make sure I'm still like talking. Okay, cool. So those were some just general examples of how to do some of these different like application problems. Again, when we're dealing with more with physics stuff, I strongly recommend just listing out all the different variables that are sort of possible for you to plug in for, stuff like that. Just a second. So, yeah, I don't really have much more to say other than definitely make sure you sort of have these different formulas that I've shown you in your back pocket, and always just look for ways to sort of plug in variables so that you can figure out how to sort of solve for what the problem is asking for. Always thinking about, okay, what do I have to plug into these different functions or formulas, and then what do I want to get out of them? That's always a good way to sort of tackling any of these different kinds of problems. It will definitely be beneficial to you in the future. There's a lot of these things in the textbook that I strongly recommend you go over, as well as some more in-depth explanation as to why these formulas work the way they do. So definitely, if you're sort of like confused about like, okay, why does this all work at all? Either do that, or if you really need some more sort of direction, reach out to me and I can find some like YouTube videos or something to ask you about it, or go to Bradshaw's office hours where I'm sure he'll help you through these things. So yeah, that's all I really have to go over. I might cover like pumping and stuff in a future session, but I don't think we've actually gotten to that in class. So I might do that on like Thursday alongside maybe some other review. And I'm gonna be sending you guys some more like final exam review material in the meantime. And I'll probably be holding like long form office hours the few days we have off before final start, just so that you guys can sort of get some last minute studying and so I can provide you with like some kind of review material, stuff like that. Okay, thanks so much everyone. Have a good one.